Hi, welcome. Today we'll continue with twisting round bars, the second statically determinate example. Today we'll work a bit on the symbols. We need to calculate the maximum value of moment m that can load the shaft shown in the figure below and the total angle of twist of the shaft. Here we only have the symbols dl meaning diameter, segment length, Kirchhoff's modulus, and torsional strength. Let's describe these segments A, B, C, D in some way to make it easier for us to write everything out later. Let's mark the reaction at the support from the previous example if I remember correctly. Maybe we didn't calculate it there. Let's calculate it for practice. I'll remind you of the notation. When we were thinking of cutting from the right side, positive moments are directed outward. The turning moment directed outward is positive from the left side also outward. Positive inward are negative, of course, if we assume the axis is directed to the right. And the right-hand rule. The moment MA, which I marked, is positive. The moments 3M and M, which are in the task, are negative. I mean, perhaps the moment MA is directed to the left, the moment directions 3M and M are to the right. Whether positive or negative depends on which side we're looking from. So we calculate the reaction at the support. The sum of twisting moments is equal to 0. So MA positive minus 3M minus M equals 0. From this, Massachusetts has the value of 4M. Let's take a look. Make these cross-sections from the left side. So MA is directed outward. I got positive 4M, which is consistent with the direction I assumed. If I got negative 4M here, it means I assumed the wrong direction and it's the opposite. I assumed it positive as the direction is outward looking. From the left side, the twisting moment is positive. So the moment in segment AB making a mental cross-section is only this moment MA. The moment in segment BC is already this positive moment MA minus 3M, because 3M is directed towards the cross-section. And the moment in segment CD is the same as the moment in segment BC. And we have a new segment because the cross-section changes. Because here we have... Oh yes, I haven't mentioned that yet. I mean, with such drawings, this is technical drawing. There's the axis of the whole drawing, and only the upper half is shaded. So we have a rod, as if we've cut it in half, and shaded only the upper part of the section. It's something like that. Then imagine that we rotate the shaded part 360 degrees around the axis of the entire drawing. Then we'd have a full rod here. And here we'd have a rod with an indentation. And the external diameter is 2D, and there's also an internal diameter marked D. So there's a new interval because the section changes. So from the strength condition, we need to calculate this moment. What is the maximum moment we can apply here? That is, the maximum shear stresses on the entire rod should be less than or equal to the twisting strength. Shear stresses, I remind you, are the twisting moment divided by the indicator of twisting strength. So now we need to... The twisting moments I've already listed in 3 intervals. The indicator of twisting strength. It will be the same on the AB and BC intervals because it's the same section, a full circle, a full cylindrical rod, and here with an indentation. So using our tables, we look at the twisting strength indicator for a circular section. Here it is pi d to the third over 16, whereas d, well, it's the diameter marked here. For us, it's 2d, right? So the AB indicator is equal to the BC indicator, 2d to the third over 16, simplifies to pi d to the third over 2. Now the annular section, like we have on the CD interval, so the strength indicator on the CD interval, here it should be CD, sorry. So we have such a formula, that is the large diameter to the 4th power, our large external diameter, meaning it is 2d, minus the internal diameter, which is d to the 4th, over 16 times the large external diameter. It reduces to this form. Let's move on. So we have the indicators calculated, we can calculate the shear stresses. Now we need to consider, because what we are interested in are the maximum shear stresses, right? Strength condition. So we want to determine the maximum shear stresses are located. Let's think about it. The twisting moment. What do the stresses depend on in general? On the twisting moment, it is the indicator of twisting strength. So the larger the moment, the larger the stresses. The smaller the indicator, the larger the stresses too. Or the larger the indicator, the smaller the stresses. So moment indicator on the AB and BC intervals is the same because it is the same section. Now, the greater the moment, the greater the stresses. That is, it is larger on the AB interval, so we don't consider the BC interval at all yet. Now we need to consider the CD interval. Here we have the same moment as on interval BC. Although it is 4 times smaller than on interval AB, there is a different cross-section here. Here it is an annular cross-section, so I think it would be appropriate to check both interval AB and interval CD, and compare where the shear stresses are greater. So let's do that. Shear stresses on interval AB, we take the twisting moment over the index. Pi d cubed over 2. The 2 from the denominator moves to the numerator of the entire fraction. We have 8m over pi d cubed. Shear stresses on interval CD, moment on this interval, and torsional strength coefficient, 32 in the numerator. So we have 32/15, which is a bit over 2 here and 8 there. So actually the greater moment here decides. So our maximum stresses are the stresses from interval AB. And now these stresses from interval AB are to be less than or equal to torsional strength, because that's the strength condition. So, and here we are working with symbols, so yes. We have to calculate MD is given and torsional strength is given. So this needs to be rearranged to calculate M. So we must multiply by the reciprocal of what's next to the moment, which is pi d cubed in the numerator, 8 in the denominator. The fraction gets simplified, leaving M, and we'll have that M should be less than or equal to. And now add pi d cubed to ks and divide it by 8. I hope you understand what is meant. And that is the first part of the task. Now the second part of the task, which is the total twist angle. The twist angle recalls the formula, which is the twisting moment times the length of the interval divided by the Kirchhoff's modulus times the moment of inertia for torsion. And the moment of inertia for torsion also depends on the diameter, so it will be different. It will be the same on the first and second intervals, but different here in the annular cross-section. So now the moment of inertia for torsion, circular cross-section, pi d to the 4th over 32. Reminder d is our 2d. It reduces to pi d to the 4th over 2. Pi d to the 4th over 2. Annular cross-section, moment of inertia for torsion. We have for the large outer diameter. Substitute 2d for the inner d. And the denominator is only 32. It reduces to this form. Now the twist angle on interval AB, which will be the twist angle of section B relative to section A. Here, I already take into account the entire length of the interval L, because the twist angle can also be calculated with the integral, which I will present in the next indeterminable static example. But generally, we will calculate the integral if a non-concentrated twisting moment is applied, as we have here. Only we must calculate the integral when we have a continuous twisting moment load, but we will not go into that for now. We can calculate this way when we only have concentrated moments, no problem. So, the angle of twist on the AB segment, we take the twisting moment from this segment, 4m, the length of the segment L, and indeed all. 3 segments are L, Kirchhoff's modulus, and the appropriate moment of inertia for twisting, which we calculated. 2 to the numerator, and we have it. The angle of twist of section C relative to section B, well, we have it. I probably don't need to explain. You already know what's going on. And the angle of twist of section D relative to section C, well, moment M, segment length L, G, and here we remember to substitute. And there's an error here. CD should be here, the moment of inertia of segment CD. And we substitute just this moment of inertia of segment CD. And we have it calculated. So now the angle of twist, the total angle of twist. From the method of superposition, these are the relative angles of twist of our 3 segments. So we just sum up these results. And that will be the total angle of twist. Well, I put this into a calculator. You can of course do it manually if someone prefers. 182 times m times L over 15g. Pi d to the 4, and that's it. The task is solved. It's not particularly difficult. If you have any doubts, I encourage you to ask questions under the video. Like us on Facebook. Visit our website, which has many examples of strength mechanics and structural mechanics. Subscribe to our YouTube channel to stay updated with new content, of which there will really be a lot. And thank you for your attention today. Take care, bye for now.